Hi students, in today's lecture we will discuss how the helicity of electron neutrino is measured experimentally. First of all, we will define what is helicity. If S is the spin of the particle and P its linear momentum, then helicity is defined as the dot product of S and P divided by the product of magnitudes of S and P, which can be written as S into P into cos theta divided by S and P, which is equal to cos theta. Now two cases arise. One, when the spin of the particle is in the same direction that of the linear momentum of the particle, where theta will be 0, and that's why h is equal to plus 1, and that's why this case is called positive helicity. And in second case, s is just in opposite direction to the linear momentum of the particle. In that case, theta will be 180 degree and h will be minus 1. That's why this case is called negative helicity. Now let us come to the original experiment performed by Goldhaber to measure the helicity of electron neutrino. Let us first discuss the principle of this experiment. Let X is a nucleus with spin 0 which captures one of its k-shell electron to turn into its daughter nucleus Y, which is produced in excited state and has spin 1 along with an electron neutrino. If we apply the conservation of linear momentum on this process, since electron capturing occurs for k shell, that is in L is equal to 0 state, that is the nucleus X and electron are at rest with respect to each other, then the linear momentum of this state will be 0. And because of conservation of linear momentum, the linear momentum of final state, that is excited state of Y and electron neutrino, will also be 0. And therefore excited nucleus Y and electron neutrino will move into opposite directions. Also, since Y is in excited state, it will come to ground state with spin 0 by emitting a photon. And if photon is produced in the same direction in which excited state of Y is moving, then this photon will also have linear momentum opposite to that of electron neutrino. Let us further apply the conservation of angular momentum to this process. The whole process can be seen like that. The nucleus X captures electron and a daughter nucleus Y is produced in spin 0, a photon and an electron neutrino. The possible Z components of spin of X is 0 because the spin of the X is 0. Possible Z components of spin of Y is also 0 because the spin of Y is 0. Possible Z components of spin of electron are either plus 1 by 2 or minus 1 by 2. Possible Z component of spin of photon is plus 1 or minus 1, and possible Z components of spin of electron neutrinos are plus 1 and minus 1 by 2. Now if we apply the conservation of angular momentum on this process, the spin of X is 0 and plus the spin of the electron 1 by 2. In the final state, the condition will be the spin of Y is equal to 0, the spin of photon will be plus 1, and the spin of electron neutrino will be minus 1, and on both sides the angular momentum is 1 by 2. In second case, the spin of the parent nucleus is 0 and the spin of electron is minus 1 by 2. To conserve angular momentum, the spin of the Y is 0 and the spin of photon will be minus 1, and the spin of electron neutrino will be plus 1 bit. Again, we can see that the angular momentum on both sides is equal. So there are only two conditions, and we can see that if the spin of the photon is plus, then the spin of the electron neutrino is minus 1. And if the spin of the photon is minus 1, the spin of the neutrino is plus 1. That is, whatever the spin of photon is, the spin of electron neutrino is just the opposite of photon. If we apply these two conditions, that is, the linear momentum of photon is just opposite to that of electron neutrino, and the spin of the photon is just opposite to the spin of the electron neutrino, then we can see that the helicity of photon is just the same as that of the helicity of neutrino. How? If the spin of the photon is in the same direction that of its linear momentum, then the spin of the neutrino will be opposite to the spin of the photon, and the momentum of the photon will also be opposite to the momentum of photon. In this case, the helicity of photon is plus 1, that is positive helicity, and the helicity of neutrino is also positive. Second case could be that the spin of the photon is just opposite to its linear momentum, and since the spin of the neutrino is opposite to the spin of photon, and linear momentum is also opposite to the linear momentum of photon, so in this case the helicity of photon is negative, and therefore the helicity of neutrino is also negative. So therefore, if we can measure the helicity of photon, we can measure the helicity of neutrino. One more condition that has to follow by these nuclei is that the neutrino has to be produced in resonance. So there are couple of conditions that have to be fulfilled by the parent nucleus and the daughter nucleus. And what these conditions are: the parent nucleus must have spin 0, it must undergo K-shell electron capture, the excited daughter nucleus must have spin 1, it must emit photon before it comes to rest, that is resonance scattering, and photon must be capable to exhibit resonance scattering. So it is just impossible to find all of these conditions in one nucleus, but Goldhaber and his co-workers found a nucleus which is called Europium 152, which exhibits all these conditions. So it is rightly said that fortune favors the bold. The Europium nucleus has spin 0, and it captures one of its K-shell electron and turns into excited state of the samarium with spin 1 and an electron neutrino. And the samarium 152 in its excited state emits a photon and comes to ground state with spin 0. Now, how Goldhaber and his co-workers found the helicity of photon, the arrangement can be seen in this picture. They took a Europium salt and it was shielded with an iron compound, and it was also put in magnetic field in upward direction. Now see, if Europium Let us see the experimental arrangement once again. The uranium salt is put inside an iron slab and a magnetic field is applied upward. Because the magnetic field is upward, the electrons in iron slab will have their spins downward because of ferromagnetism. Now when a uranium nucleus captures one of its k shell electrons, a samarium in its excited state and a neutrino are produced. If the direction of neutrino is upward because of conservation of linear momentum, the direction of samarium will be downward. Now, because this samarium nucleus is in its excited state, it will emit a photon to come to its ground state. This photon either will be moving in the direction of neutrino or in the direction of samarium, that is downward. Now, let us consider the case when photon is moving downward. There are two further cases. One, that photon is moving downward and its spin is also downward, that is -1. And second case, when photon is moving downward and its spin is upward, that is +1. In case B, since the spin of the photon is upward and the spin of electron is downward, this photon while passing through iron will be absorbed by this electron and the spin of electron turns +1/2 and no photon will pass through the iron slab. In second case, since the spin of the photon is -1 and the spin of the electron is -1/2, this photon cannot be absorbed by the electron and this photon will pass through iron slab as such. When this photon is bombarded with the samarium salt, it is scattered towards the sodium iodide detector, which will detect this photon. Now, if this photon passes through the iron slab, its helicity will be positive because the direction of photon and the spin of the photon are in the same direction. But in experiment, Goldhaber and his co-workers observed none of this kind of photons. That is, there is no photon with helicity positive. As we have already discussed that the helicity of neutrino is the same as that of the helicity of photon, and there is no photon of helicity positive. Therefore, there is no neutrino with helicity -1. Therefore, the only photons that are being produced in this process are have helicity -1, and therefore the helicity of neutrino is -1, that is negative. So this is how Goldhaber and his co-workers found the helicity of the electron neutrino.